Okay, sorry, I had to break it up into two videos. Number 5. An object moves according to the graph shown on the right. What is the velocity of the object at 1.5 second mark? Alright, well, this one's very simple because this is a velocity graph. So at the 1.5 second mark, that would be right here on our time axis. What is the velocity? You go up and you see that the velocity is right here, which would be at 3. So our answer for that one should have been D. Part B, what is the object's displacement from 0 to 2 seconds? So displacement just meaning distance, how far it's been displaced. On a velocity graph, that's area. So from 0 to 2 seconds, they're talking about what is the area of this triangle that's formed. Okay, so the area of a triangle is 1/2 base times height. Our base is 2. The height of this triangle goes up to 4. So half of 2 is 1. 1 times 4 gives us 4. If you answered 8, you probably forgot to take the half for that triangle. All right, next problem. Problem 6. Jasmine starts at a speed of 0 and speeds up to a positive velocity. Draw a motion diagram. Alright, so a motion diagram, this is a very simple one. Oh, I guess we're going red. I'm going to undo that. Okay, so we have our axis. You have to label your axis once again. So make sure you have a 0. You have an X. It's saying that she starts at a speed of 0 and speeds up in the positive direction. If that's the case, then we are going to start here and start with our dots close together. They get further apart as it goes to the right. So then we have arrows connecting those. These are called our velocity arrows. I'll make them in blue. They're going to the right. And our acceleration arrows, which everyone always forgets. Since it's speeding up, the acceleration is the same as the velocity, so they're also to the right in this case. There's your motion diagram. All right, part B, draw a position versus time, velocity versus time, and acceleration versus time to show that motion. So before I even make any of these graphs, I probably want to put the labels on these first, on the axes. So this is going to be my, so getting used to this program, guys, sorry. Here we go. This is going to be our position versus time graph. This will be our velocity versus time. And the last one, this will be our acceleration. Okay, on our motion diagram, we showed it starting from a position of 0. So let's do the same here. If something is speeding up as it's going in a positive direction, we need to show a slope that is curving on this. So it's starting off flat because it starts off slow, but as time goes on, it gets steeper. So it's curving upward. It should be nice and smooth, so maybe better than mine. But you should have it flat and then get steeper and steeper as it goes in a positive direction. The velocity, it started with a velocity of 0, so we start there, and as time went on, it got faster and faster in the positive direction. So from that speed of 0, the speed increased upward, and as time went on, it got faster and faster. Our acceleration, we look at this slope that we just made. This slope is positive and constant. So our acceleration is positive, starts up here, and constant, meaning it's a flat line. So if you don't remember it, if you can't look at this and tell this is a positive slope, look back to your motion diagram. We had arrows for our acceleration that pointed in the positive direction. So that's why you need to show a positive acceleration on this graph. All this motion, all these graphs, and the motion diagram, it all matches. All right, problem 6 again, I suppose. Sorry, there's a typo there. Consider the following graphs, noting the different axes, position, velocity, and acceleration. Part A asks you which of these represents motion at a constant velocity. Okay, so this is a position versus time graph. We have one straight smooth line, one straight slope. So that's showing it's going at constant speed or constant velocity. So yes, graph A is going constant velocity. B, we have a smooth line again, but now this is a velocity graph. This is showing a velocity that is speeding up, getting faster and faster over time. So no, that is not a constant velocity. Whereas C, it is a positive velocity and it stays at that same positive velocity. It's staying at that same speed the entire time. So for C, yes, this is going in constant velocity. Let's circle that one. D, acceleration. This is showing acceleration that's increasing. So not only is it getting faster, but it's getting faster at an increasing rate. So D would not be a constant velocity. E for acceleration. If you have a constant acceleration, that means you're getting faster and faster at a constant rate. So your velocity is not staying the same. So the only two you should have circled on part A were A and C. Those two show a constant velocity. 7. Which one represents a constant non-zero acceleration? Okay, so if something's going a constant speed, like we said on A and C, it can't have a non-zero acceleration. So we know those two are not going to be it. So let's look at graph B. Graph B, speed is increasing at a constant rate. There's a slope to our velocity graph. That's telling me that there's a nice constant acceleration. So I'm going to answer B on this one. For graph D, the acceleration is increasing. Since the acceleration is increasing, that's saying that the acceleration is not constant. They wanted a constant acceleration. The acceleration is not constant on that graph. So D is not one of our answers. E would be. It's a constant acceleration. It's staying at that same acceleration for the entire time. So the two you should have circled on 7 was graph B and graph E. Okay, next problem. A bullet is shot into a pool. The bullet enters the water with a speed of 350 meters per second and slows to a stop in 1.5 seconds. Calculate the acceleration of the bullet underwater. Alright, so if it started at a speed of 350 and it ended at a stop, it ended at a speed of 0, the change of velocity for that bullet, if it starts at 350, ends at 0, is a negative 350. It slowed all the way down. It did this in 1.5 seconds. If they want acceleration, we have an equation for it. Change in velocity divided by time. So our change in velocity would be the negative 350 divided by the time it took, 1.5 seconds. So we will get a negative acceleration because this is slowing down. And 350 divided by 1.5 will give you a negative 233.3 repeating. So we can just put 0.33. And the label for that, this is an acceleration. So meters per second squared. Don't forget your labels on these. How far did the bullet travel underwater during that time? Okay, well, we have a distance equation, equation number 2, which tells us velocity initial multiplied by time plus 1/2 acceleration multiplied by time squared. Velocity initial, we said, was the 350. So we're plugging that in for VI. 350 multiplied by the amount of time it was underwater, so 1.5 seconds, plus 1/2 our acceleration. Now our acceleration is what we just solved for, so it's that big number, negative 233.33. You can write that as well. Multiplied by our time, which is still the 1.5 seconds. Time is under the water, but we have to square it on that second half of our equation. Okay, so 350 multiplied by 1.5 will give you 525. On the second half of this equation, make sure you are squaring this first, square the 1.5 first, and then multiply across. So 1.5 squared gives you 2.25 times the 233 0.33, and you take half of that, you should have gotten a negative answer when you multiply those three things. So it's a negative 262 point, I'm going to round it to 50, around that. So now we have two numbers that we need to subtract. So our final answer, 525 minus the 262.5 will give you that same exact answer actually. So the distance will be 262.5 meters. If you got something extremely close to that, but just a little bit off, we probably just rounded differently. So if your answer is really close to that, you'll still get that full credit. So 262.5 meters. All right, our last problem. An exceptional drag race car has an acceleration of 28 meters per second squared. From rest, what speed can the car reach in 10 seconds? All right, so we know acceleration. We know it starts from rest, so we know velocity initial. What speed can the car reach in 10 seconds? They're asking us for velocity final. We don't know what that is. We do have an equation for it, though. It's motion equation 1. Velocity final is equal to velocity initial plus acceleration multiplied by time. And we know all three of those things. So let's plug them in. Our velocity final will equal velocity initial, started from rest, velocity initial is just 0. Plus our acceleration for this car is 28 meters per second squared, multiplied by our time, which is 10 seconds. So this is a fairly easy problem. Since we know this is 0, that kind of just drops out. Our final answer for velocity final will just be 28 times 10. So 280 is our answer for this last problem. This is a velocity, so make sure you have a label, meters per second. All right, guys, I hope you did well. Look back over this, make sure you understand that all the processes on all of the problems, and you should be good for tomorrow's test. Good luck.